Oh wait, this is, sorry, 1 second. I just realized something. It's the wrong talk. This might be better. Okay, so I'd like to thank the organizers for inviting me. And I'm going to talk a little bit about, there's this theme that's starting to happen of people trying to take what's been done on graphs and extend it to higher order interactions, higher order models. And there are a few people in this room who are thinking about this. And then this falls under that category. This is joint work with my former student, John Steenbergen, who's now at UIC, and Carly Clivens, who's at Brown. And just to show, spectral graph theory seems to have become quite popular. There's a wonderful book by Fan Chung, and then you can talk about page rank and how relevant it is. And this is, I guess, figure 1 from the paper by Jeff Cheeger, where he related the Laplace-Beltrami operator to, and eigenvalues of it to the isoperimetric constant. And just something that I kind of thought was kind of cute and maybe appropriate for here is we are in the Simons Institute, and when he talked about this problem, this is something that Jeff Cheeger, talked to Jim Simons about anyways, but we'll come back to a variation on this picture later on, but this picture will be important. So it has many applications, and just to list a few, Markov chains, we saw some of that, clustering, ranking methods, dimension reduction, semi-supervised learning is something I'll come back to, and it's also been used in isomorphism testing. And I just wanted to show one example, and this is just to advertise what Misha had done. So this is a dimension reduction method, Laplacian eigenmaps, where you take your data, you construct an association matrix, you compute the graph Laplacian, you look at the top eigenvalue, well, you look at the eigenvalues and eigenvectors of that, and then you'll notice that the first eigenvector is all ones. It corresponds to the eigenvalue of 0, and then there's this gap. We'll be talking a lot about this gap, lambda 1. You can map these points into the top k, looking from the left eigenvectors, and this has some geometric, hopefully, intuition. And here's just a nice video that was made by Dinod Shindaran and Partheniogi, where you have a bunch of images of digits. This is a digit database. This has been projected into 3 dimensions, and we're going to be zooming in here, and you're just kind of seeing what the actual structure is. And this is just to argue that for things like dimension reduction or clustering, the spectral methods, may make some sense again. One argument for why this may work, and if you want to kind of make this semi-topological, is, well, if you want to find near-connected components, this is looking for near-zero homology. So this, again, you can think of as a dumbbell, and you can ask, okay, what are the near cuts of this, right? And if you have data, this can be reformulated into a clustering problem. You have a bunch of points, you want to cluster them, and so that's one problem we'll talk about. That's kind of the Cheeger notion of a cut. And the other problem we're going to talk about is defining random walks on simplicial complexes. So again, going from half to higher order forms. And this is the idea of label propagation. And this is something that Jerry had worked on a while ago. And the idea is if I have some labeled points here, class 1, class 2, the blue squares are unlabeled points. Somehow I can run a random walk or diffuse information, and these will all get colored red, these will all get colored black, and we'll come back to that for higher order notions. So coming back to graphs, if you want to talk about something called the Cheeger number of a graph, what I have is I have a bunch of vertices. They're connected by these edges. And what I'm asking you as the Cheeger number is, okay, this is the number of edges between S and its complement. I put a delta here because this is going to be what's called a co-boundary operator. Soon, I'll define it. But I want you to kind of get you thinking in terms of chains and cochains. So that's why there's a delta, and it's a cardinality of that. And you're just looking at the minimum of the cardinality of S and S complement, and you can think of as this as a cut. And if this is 0, then the graph is disconnected. So this is basically an isoperimetric constant. One can think of a relaxation of this, or a Rayleigh quotient version of this, and this is what's called sometimes a Fiedler number or the algebraic number. And here, what I'm doing is I'm relaxing this. I'm putting function values on the nodes, and I'm looking at just the distance, or the square of the function values for 2 adjacent nodes squared, divided by some notion of the norm of the function values, and you want this perpendicular to the 1 vector. this idea of being perpendicular to the one vector will come up again in a more abstract sense. And you can think of this as a relaxation of this, of the previous problem. And if lambda again is 0, the graph is disconnected. And the classic form of the Cheeger inequality, at least for graphs, was so Noga alone studied this for expander graphs. Millman was very interested in kind of some notion of geometry of this. Lawler and Sokol looked at this for the case where you also had absorption. And Percy talked a little bit about this the other day. Fries, Kannan, and Poulsen studied this for Markov chain theory. And again, there's very nice work by Diakonis and Struck on this as well. And basically what you can say is you can bound that eigenvalue by the isoperimetric constant. So this was kind of the main idea of the Cheeger number. And the reason why this became relevant often is initially in studying expander graphs. So if I have a family of random graphs, let's say a sequence of d-regular graphs increasing with I, expander graphs are going to be those that as the sequence gets larger, all of these have a positive cut, okay? And one of the uses of this was, this could be, the isoperimetric constant may be hard to prove that is greater than 0 for this family, but you can show that often you can show that the spectral gap is greater than 0 using simpler techniques. So that was part of the idea and the motivation. So the other kind of idea and direction is there's a very natural relation between the harmonics of the graph Laplacian and the stationary distribution of a random walk. So if I give you an association matrix, I can turn this into a probability transition matrix, and I can relate and I can work out the stationary distribution here, and I can tell you that the harmonic is related to that stationary distribution. And we'll come back to this type of statement, but again, not on graphs, on simplicial complexes. Okay. So this is what I was just saying. We're going to try to move from graphs to simplicial complexes. So you might have, triangles, tetrahedrons, so on and so forth. And one reasonable question is why? So here's a problem. This is a problem that's a sensor network coverage problem. And these are problems that some people in algebraic topology have been looking at. This is Rob Greist and Vin De Silva have done some very nice theory on. And then other people like Ali Jedbabai and some of his colleagues have been looking at applied versions of this problem. And you can think of this, you're flying a plane around and you're getting information on local areas, and you don't have GPS. But what you do have is the connectivity locally. And from this, you want to do computations to figure out, is there a hole? So that's a version of this problem where you start actually looking at these simplicial complexes. There have also been versions of this problem which are ways of thinking of higher order notions of page rank. So think about a bunch of authors. Say these 3 people have published 10 papers together. Okay? These people have published 4 papers together. You can think of building this out, and then you can ask, okay, how can I think about some type of ranking structure here? So this is a motivation. And the ranking problem, I think the next talk, actually I don't think, the next talk is by Lekang Lim, and he will talk about the ranking problem and make that more concrete, okay? So just for motivation, and that's probably about as much motivation, at least in terms of applied problem, I'm going to give in this talk. But we're going to come back and think about some notions of homology. So here we're just saying that Betty 0 is the number of connected components, Betty 1 is the number of holes, and Betty 2 is the number of voids. And so this is a way of characterizing this. And what we'll come back to is these numbers can be thought of algebraically, and I'll tell you how that's done. And these numbers can be thought of algebraically by looking at a higher order notion of the Laplacian, something called the Hodge operator, and we'll come back to that. But the intuition I want to say is spectral clustering in a way is looking for near 0 homology. That is one perspective on it. I'm not saying it's the only, but that's one perspective on it. And so what happens if we do want to do spectral clustering but to find near holes, right? Can you use a higher order notion of the Laplacian to do that? So that's one way of thinking about this problem. Okay. So the picture that I want you to think about is the dumbbell, right? The diffeomorphism of the dumbbell was very useful motivationally to think about Betty 0 and near cuts there, right? So now I want you to think about a hockey puck right? Take the middle of it and start pinching it down towards a torus, okay? And that's the analog notion for near one homology. Okay, so that's a picture, kind of the analog of the Cheeger dumbbell that I want you to have, and you can do that if you had some dough or donut material. So this is a picture. This is actually a pinched hockey puck. Doug Arnold generated this using finite element methods, and what I'm showing you is what the eigenvectors of the one Laplacian look like. I'll formally define all of these, but I wanted to give you kind of a picture. And what you see is these are kind of notions of flow, and what you want to do, if you want to think about cuts, it's like basically like cutting the flow. But as I pinch down and more, the flow is going to get stronger and stronger, is kind of the idea. And one can do the same thing and think about it this same thing. This is actually, we're taking a solid hockey puck. Okay, it's solid. We're taking the middle and we're pinching it down, and the amount of pinch is the thickness in the middle is the x-axis. I should have written the axis, I'm sorry. And the y-axis is the eigenvalue. Okay, so you figure when it gets pinched down completely, right, the eigenvalue should go to 0, and that's where the distance is 0. And as I get it bigger and bigger, it gets increases. So this is just, again, same type of picture, numerical illustration of what happens with that. Now, one thing that's interesting is if I did this with a non-solid hockey puck, if I just did it with the shell of a hockey puck, anyone have a guess what would happen to that eigenvalue? What would it do? It would do nothing, right? Because it's diffeomorphic to a sphere, right? It would do nothing until it pinches through. Okay, so again, just some pictures. So related work. So in a very kind of discrete perspective, Dadzuk and Patodi studied Riemannian structures and triangulations of manifolds. I would say kind of from the theory field, there's really beautiful ideas by Lignal and Meshulam studying, they had a random complex model, which I'll show you later on, and really trying to understand properties of that. And one way you can think about that is extending the Erdős-Renyi model on graphs, right, to these higher forms. I'm going to come back to that. This is work by Dominic Dotter and Matt Kale on defining co-boundary expanders. I'm going to touch on this as well. These are negative results on Cheeger numbers. This is another paper looking at Cheeger isoperimetric inequalities, but it's a different notion of Cheeger numbers than we're going to talk about here. This is work we've done, and I'll tell you what it is. What we've done is actually very related to some things that Fan Chung has done on random walks and local cuts on graphs and Dirichlet graphs, and I'll mention some of that later on. And then there's this kind of, Avi Vitkerson's worked on this, and there's work that Prasad's done that's related to this. So this is kind of just a short list of some of the simplicial complex Laplacian work. Now the random walks on simplicial complexes, there's less. If you don't think about very abstract versions of it, which are random walks on groups and things like that. And that's some work by Oli Parvzhinchevsky and Ron Rosenthal, and work that we've done. And these are quite related. And so when I tell you about our work, you'll effectively also learn about their work, and I'll tell you how. Okay. So let me just give you some definitions. So a simplicial complex, convex hull, k plus 1 affine independent points, we'll just define them u0 through uk. A face of tau, a face tau of sigma is a convex hull of the non-empty subsets of ui. So again, when we define an abstract simplicial complex, it's a finite collection of simplices such that any face of a simplex in K is also in K. So if I gave you a triangle, I couldn't remove one of the edges. That would not be legal. And the intersection of two simplices is a face of both simplices. Can't take a triangle and just stick an edge right in the middle. That would not be legal. Okay, so that's kind of what we're saying. Simplicial complexes tend to be oriented. So you have this notion you can have orientation this way or that way. These are equivalence class of even permutations. This orientation is going to arise again. When I talk about random walks, this orientation is going to cause something that looks different than the standard random walk on the graph, and you'll see how. But this idea of orientation will come up, and it's something that's a little bit different than for graphs. So there are kind of two ideas. There are two types of operators. There are chains and cochains, boundaries and co-boundaries, and we'll talk about that a little bit. So if this is my simplicial complex, what does a boundary do? It takes an edge, takes it into two vertices, right? So boundaries always take higher order complexes into lower order complexes, if you want to think of it as a map. Here, same thing applied to a triangle. We're breaking it up into these. And if you'll notice, typically, not typically, almost always, we'll write things as alternating sums. Again, because of this algebraic topological construction, you have these alternating sums. You'll see them again and again. Okay. So again, I told you we're going to have chains and cochains. So if I have a simplicial complex of dimension m, what I think about in terms of chains, these are linear combinations of oriented case simplices. F is going to be a field. I'll tell you why I'm just calling it a field in a second. And then you have cochains, which are functions on these simplices, okay? So one's a linear combination of the simplices. The other ones are functions on the simplices. Now, the reason why I'm using a field, F, is I'm going to use two fields. One's going to be the reals. The reals are going to be used when I'm thinking about the Rowley quotient, the relaxation, to get that eigenvalue, okay? And the other one I'm going to use is Z mod 2. Z mod 2 is going to be used when I want to get the isoperimetric, right? So you think about that zeros and ones, you're doing basically binary addition, and it's just splitting things up into sets. So that's the logic there. Okay, so chain complex, like I said before, you have these chains, you're applying these boundary operators, and they're moving you down. Cochain complex, similar idea. You have these chains, you're applying the co-boundary operator, and you're going up. So almost all the results in this direction was first done looking at cochains, because when you think about a graph, you're really looking at a cochain, because you're not going to be going down, because then you're going from vertices to, in a way, nothing. Reduced homology, it is formally nothing. But when you think about going from the vertices to an edges, you really are thinking about a cochain. So a lot of this machinery was first developed for cochain complexes. Now, the boundary map can be defined, again, as this operation, which is you take a point out, and then you take the alternating sum of the subvertices. I'll actually show you a picture of this so you don't have to parse it. And now, this is in red. I'll tell you why this is in red. The co-boundary map is sticking it in and then doing something very similar. It can also be thought of the transpose of the boundary map. Now, in the context that we'll be talking about today, this statement is a little bit shady. These two are transposes, that's certainly true. Formally calling this a boundary and a co-boundary map is it's developed in a theory called de Rham theory, and it's a beautiful differential theory, and you need something called identification of these vector spaces, right? And in a way, we don't have clean identification of these vector spaces. We forced them. And because of that, some of the results we're going to get, the reasons why we can't prove things, Cheeger inequalities in certain cases, I think arises from that. And I'll give you a little bit more intuition about that, but that's why it's a little bit in red. I was just afraid if there was a real differential geometer, they'd come after me. And
the index go from 0 to k instead of 1 to k?
It should be, yeah. Yeah, sorry about that, yeah. Okay.
I think you have the right t-shirt.
I do. Yeah. I try. And so you can think about the homology and cohomology vector spaces in terms of the kernels of these operators, modulo the images from coming from above, and similarly for the cohomology, you can define it this way. And we'll talk a little bit about that. Now, I wanted to show you a picture. So if this is my simplicial complex, and these are the values I've put on it, right, with these orientations, if I hit it with a boundary operator, and I'm working in the real field, basically, this is 3, 1, 1, 2, you can do the addition yourself. That's what's going on there. And if you do Z mod 2, you get something similar. You break it up in terms of, now you're just doing binary addition, and one can similarly look at what happens to what the co-boundary operators do, and for both in the real fields as well as in Z mod 2. Just give a little bit of an intuition. Now, something called the Hodge Laplacian sometimes called the Combinatorial Laplacian, and I have a, there are two parts to it. Some of my colleagues call them up and down. I'll explain to you why. But more formally, what you're saying is, It's taking a K-form, it's spitting out another K-form, and what it's doing is the up part takes it, moves it up by the co-boundary, and then brings it back down by the boundary. So it goes up and down. And this will be relevant in the random walk. I'll actually show you a picture of what it means. But think about it this way. If you had vertices, the first part would be taking the vertices to edges, and the second part would be, in a way, bringing it back down. That's kind of the analog. And then there's a down part, which takes it from, you have the boundary operator in K, takes it to K minus 1, and then you have a co-boundary operator in K plus 1, so it moves it up. So another way you can think about that, think about a circle, think about tessellating the circle. You have faces, right? What you could be doing is basically you'd be moving from a face down to an edge, back up to another face. That's another way you can think about it. Okay? So this is a Hodge Laplacian. Now, this is an important theorem. This is a theorem by Ekman, and what it tells you is the Laplacian has a very nice property in that it breaks up this space into a direct sum of three parts. One is the kernel of the Laplacian, and then the image of the co-boundary coming from delta k minus 1, and the image of the boundary operator. And these will all give you some notion of the homology. Now, a very nice picture that I think gives you some of the intuition of what this type of theorem does in, let's say, for the one Laplacian, is something I stole from Pablo, which is, if you think about the vector space C1, you can break it up into parts that are harmonic flows. This is a kernel of the Laplacian. Parts that are gradient flows, right, which is the image of delta 0, okay? And then parts that are basically curls, which are the image of the boundary operating on 1. So that's another way of thinking about it. And Leking will actually talk about this, and Leking will explain how this picture can be used to take rankings and break them apart into parts that are consistent, parts that are cycles but long cycles, and parts that are very locally inconsistent. Yeah?
Is there some pairing involved here? Because I don't understand the definition of LK, the Laplacian, LK up and then in the previous slide.
In the previous slide. What do you mean by pairing?
I mean, how do you compose delta k with the partial k plus 1?
Right. So right now, just think of it as a transpose. Okay? No, the formal question of should these be paired is tricky. And this goes back to, there's a very nice paper by Doug Arnold and others where they're doing finite mesh methods, and they want to show that in the limit you get back the eigenvectors of the K-form, or the eigenfunctions of the K-form, by doing this. And what they can show there is for certain tessellations and certain subdivisions, you don't get that pairing, right? So it doesn't quite work out. It's not consistent. And for other ones, there are, right? And so this, in a way, is I think you've hit kind of one of the main issues in all of this, right, is we forced a pairing, right? And one can ask, if I go to a true manifold, finer and finer, will that pairing be reasonable or not, right? Yeah?
The other way of saying that is that you put an inner product.
Yeah,
That
exactly.
identifies
Yeah,
the
exactly.
Once you fix an inner product, then you're like,
Yeah, exactly. Okay, so the Cheeger inequality, the way it was thought of, we knew that it held for manifold. So one question we said was, okay, if we're going to be doing this discrete stuff, let's first try and understand it on the discrete analog of a manifold. Okay, so that was the idea. So one very natural way of thinking of a discrete analog of a manifold is you take a manifold, you basically triangulate it, right? And you call that your collection of simplicial complexes. So that's kind of a geometric notion. Now what we wanted to do is we wanted to work with combinatorial notions because the proofs are much simpler. So we used what's called a pseudomanifold, which is basically what I just told you. Okay? It's just saying that I have a space, it's got a triangulation, K, okay, it's a union of all M simplices. Every M minus 1 simplex is a face of exactly 2 M simplices, and it's strongly connected. This we don't need, but we'll use. You'll come back to this. This is very much, you can think of as something like a Dirichlet boundary condition, and I'll come back and point that out. Okay, so I think I told you about orientability. So two simplices are Laura adjacent if they share a common d-1 face. So if you think about this is oriented, this is not oriented, just to kind of give you a picture. And we'll come back to that again. Okay, so the first definition we started working with is a Cheeger number on cochains. And this comes from a paper by Dominic Dotter and Matt Kale. And there are two parts of it. This is the eigenvalue part. So if I think about the co-boundary operator, okay, F is in the cochain space. I hit it with the co-boundary operator, I look at the norm of that, and then just divide it by the norm of F, okay? You can write it in this painful way, and I'll go through it. We're writing in this painful way because what happens if you don't have perpendicular, if you aren't working in some space where the normal is clear, and you'll see why I need to do that. You can rewrite this as, again, this is the same. Now you're saying find an F that's not in the image, right? And then you're adding an extra dummy G that is in the image, and you want to minimize that. So these two are equivalent. And the reason why I wrote this is that when we look at Z mod 2, because I can't define perpendicularity in Z mod 2, and the norm here is the Hamming norm, right? I have to work with this type of version. But morally, this is doing the same thing as this, right? For the Z mod 2, but because I can't define orthogonality, I'm doing it this way. Now an aside here, for those who make hair, is Ekman's theorem and the Hodge decomposition does not hold for Z mod 2. And this causes problems later on, and I'll mention that. But that's kind of a technical issue. It does for the reals. Okay. And again, I can read off cohomology by checking if these eigenvalues are 0. This is on the reals. This is Z mod 2. So one of the things you'd hope, and it's true, is that you recover the graph Laplacian. So L0 is just this part, and again, you get back your Cheeger inequality. Now, even if you have nice pseudomanifolds, it turns out that you don't get a Cheeger inequality for cochains. And what you have is, you can construct sequences, and I'll show you how, of pseudomanifolds that have the following property in that, both your eigenvalues and your eigenvector and the isoperimetric forms are going to 0, but they're going to 0 at very, very different rates is what you're finding. So in this case, one's going at a rate 1 over k as you increase k, and the other one's going much, much faster, right? So this is what you find. And the example is something that's called a stellar subdivision. And what's interesting is if you look at Doug Arnold's paper where they asked about, finite element methods and meshing it, this is one way of meshing that will not work. And the basic idea is that you take your simplicial complex, find the barycenters, and for all of them except for the outside ones, subdivide, okay? And then iterate this, and this won't work. Now, an open question is, do there exist good families, right? Somehow well defined as good, for which this type of problem won't happen. And I believe that is related to the identification issue. You need an orientation hypothesis because if things are oriented, an example is a real projective plane where your lambda is not going to be 0 and your h is going to be 0, so you need that. Now, what happens if you just completely, again, release the orientation hypothesis? And well, what you find is that this is a proof by Anna Gundert and Uli Wagner, where they use the probabilistic method to prove that there are infinite families of complexes that are not combinatorially expanding. So lambda 0, but the eigenvalues are away from 0. All of these have torsion. None of these are pseudomanifolds. And just to show a picture from Matt Kale, they're using the Lineal-Mishula model, where you throw down this object, and then I basically start throwing down random complexes, and that's what I'm looking at. Now, turns out you also need this boundary hypothesis. This is related to sometimes how we normalize the graph Laplacian. If you have a picture like this, and you just start building up on the edges and building up on the edges here, h1 is always going to be 2/3, but lambda 1 is going to go towards 0. Yeah?
So here, in order to simulate, so in the graph Laplacian, an edge is cut or not, it is being treated as something over the field F2, and that's how it's
Yeah, the Z-mod 2.
Z-mod 2.
Yeah, yeah.
Another way to look at it would be to think of Cheeger as a relation between L2 and L1. So instead of cuts, think of it as just an L1 embedding on the line.
Yeah. I mean, this is interesting. So one of the things we've been stuck with, this is relevant, is we don't have Hodge theory, right, for Z-mod 2. So the idea of going to L1 or the idea of going to a rational field and then restricting it to be, 0 or 1, things like that. We're starting to play around with that. I wish I could tell you that we've made success, but we have not. But yes. Yeah. Okay. So you can do the same thing on chains, right? Now you're just looking at the boundary operator instead of the co-boundary operator. Everything that I said is before. This is just the same exact thing except for looking at the boundary operator. And now if lambda or h is 0, I can tell you about homology being trivial. And so for this, we have a Cheeger inequality. And it looks like kind of the standard one. I think the denominator might look slightly different, and this is for an orientable pseudo-manifold. We need it to be orientable. We need it to be a pseudo-manifold. And this is a discrete analog of the Cheeger inequality for manifolds with a Dirichlet boundary condition. So if you go back to the 1970 paper, you have results for manifolds with boundary, manifolds without boundary. One can think of these as dual of each other. And we know, for example, when people study the Laplace-Beltrami operator on zero forms or functions, that this corresponds to the case with Neumann boundary conditions. When you look at them above of the full K form, it corresponds to the case with Dirichlet boundary conditions. And what's interesting or tricky is what happens in between. And there's something called the Bachner-Weizenbach forms, which I think Lekang will talk about, that happen in between and that are more kind of complicated. So, but again, you get this positive result on chains. And so that's so far what we know about these Cheeger inequalities on these simplicial complexes. I'll state some more when we conclude. Then I just wanted to give you some of the random walk stuff. I'll go through that a little bit fast. But you have an association matrix. You construct the standard transition probability matrix, right? And what do we normally ask questions about? We ask about, is there a stationary distribution? If you start at some mu0, iterate, and then you can ask a question about the mixing rate. And then often this mixing rate is a function both of the number of iteration as well as the eigengap, right? So these are kind of very standard classical ideas. Okay. There's an algorithm. It's called label propagation. Maybe in the interest of time, I won't give you the details, but the idea is you can use this random walk idea to do that classification problem I showed you earlier with the red and the black. Right? You're basically iterating random walks and looking at certain values of them. So again, like we said, the K Laplacian has two parts. You can define random walks based on each part. So if you look at the up version, right, you're going from an edge to a face back down to an edge. And similarly, you can define the down version, which is you start at a face, you go down to an edge, and then you go back up to a face. Now, we'll first define the walk corresponding to the down part. So this is a part corresponding to the chains, or this is the part corresponding to the boundary operator. So I have X is a d-dimensional complex. This is just the max degree. Now I'm going to generate a state space, which these things have orientation. Okay, so X has a bunch of complexes, and basically I'm going to double the number. Each complex is going to be written down twice, one for each orientation. Right? That's what the plus minus mean, and theta is a death state, right? Well, you'll see why there's a death state in a little bit, but this is a little bit related to what Percy talked about when you have random walks with absorption. So that's a death state, okay? So two oriented K cells that have the same orientation are considered neighbors that share a K minus one face, okay? And then my transition matrix is I can move from I can move from a positively oriented face to another one, or I can move from a negatively oriented face to another one. It's a lazy walk, so the probability of staying is p. This is my probability of moving, and this is otherwise. This is my probability of switching orientations, and this is a probability of going into a death state, which is actually a boundary. and then once you're in a death state, you don't come out. So this is basically defining a transition matrix. And my goal is to tell you that the stationary distribution of this transition matrix has to do something with the eigenfunctions of LK down, right? So I'm going to want to tell you that. And in spite of my shirt, I want to be correct. So what we typically study is you take this transition matrix, you start with an initial probability vector, and you iterate this. Now, what we're going to find, and you ask about stationarity of this object. One of the things that's kind of interesting, and we're still trying to understand, is because of orientation, the actual object that we're going to find is the analog of the stationary distribution and is related to the harmonics of the operator, is a difference between iterating on the plus-oriented faces minus the negatively oriented faces, right? And so I can think of an operator T that just looks at the difference between these two. And one way of thinking about it is just if I have two faces that have the same orientation, it's a 1. Any two that are different is -1. So now what I can do is start with an initial distribution just on any face. Okay, that's what I'm doing. I start with any face. Iterate this P, this transition matrix n times. Okay, hit it with this T. This is just the normalization constant that has to deal with what happens because of the absorption, right? And this is what I'm going to say. This is our notion of the stationary distribution, right? And it's really renormalizing just this quantity, okay? Just multiplying it by a constant. And we want to say something about the convergence of this, as well as saying how it's related to the harmonics, okay? And what you can show is if your walk is lazy enough, then this limit exists, assuming that you start at any face tau, and the kth homology group of X with coefficients in R is trivial if and only if this is in the image of the boundary for all tau. And we can also give you a rate of convergence. Now there's an interesting point here, is if I were talking with graphs, there'd be no tau, right? Because if we have a graph, it's irreducible. No matter where we start, we know that it's going to a stationary distribution, right? And I'd really like to be able to say that to you right here, but I don't know how to cleanly define irreducibility for this case. And it's because of orientation. It's not just me. Orly Pravdzinskowski and Ron Rosenthal also have had a hard time defining irreducibility because it's not just if something can in theory get to something else. Because of orientation, you can get messed up in how it gets there, right? So if anyone has a clean explanation of irreducibility, that would be great. We're thinking about it, right? So that's kind of one of the differences. Now, what was done in the paper by Pravdzinskowski and Rosenthal was for the up graph, but they never defined a Markov transition matrix. They defined something else which they called a propagation matrix, which had this form. Well, it's slightly different, but basically it had negative numbers in it, right? And the negative numbers come from this kind of switching the orientation. But once you write down this matrix B, this can be written basically in terms of the Laplacian. So this is something very much like what we see. Think about this. Forget about the stupid constant, right? You just have I minus a Laplacian, which is something we see more of, okay? So that's kind of what they worked with. So you can also work with that. Okay. Now you can do the same thing for the upwalk. Now you're looking at co-neighbors, right? And then you can define, again, this type of Markov transition matrix. And you actually, turns out, don't need a death state here. You can put it in. And I'll tell you a little bit about that in a second. So this is what they did. They used this walk, but they didn't define that. They didn't define this matrix. They defined the B version of this. And what you can say is if k is d minus 1, and every k simplex has at least one coface, then you don't need the death state, and that's the situation they were looking at. The threshold for detecting homology this is what you need for the Neumann walk, which is the one that they worked on, and it depends on k, which is the order of the simplex. When you look at the Dirichlet walk, this is the threshold of detection, and it depends on the vertex degree, the analog of the degree. So it doesn't depend on k. So these are some of the differences you have between the walks. You can similarly define a walk by with probability 1/2 moving up or down. And recently, a postdoc that works with me, Omer Bobrowski, has a cleaner formulation of this, which hopefully we'll have written down soon. You can define a propagation matrix again, and you can say something about the spectrum of this walk. In the interest of time, I'll not talk about that. So there's an algorithm. I'll quickly go through this, and I'll show you a picture. The idea of the the label propagation algorithm, again, was you have a bunch of points. You have a random graph. Some of the points are labeled red. Some of them are blue. I'm going to propagate out the red points, propagate out the blue points. If any point has a greater probability of being red, you call it red. Greater probability of being blue, you call it blue. Very roughly speaking, right? We can do the same thing here, but with propagating edges. So let me show you a picture. Actually, before I show you this picture, let me show you this picture. Okay. So this is a red edge. So this is my simplicial complex. I'm looking at triangles. This is a red edge. This is a blue edge. These have two different orientations. And what you can do is you can basically run this algorithm, which is propagating edges. So you believe the relationships you care about are pairwise relationships on these higher order structures. You can propagate them, and you can, again, do this type of labeling. So this is an example of edge propagation. And what I wanted to show here is this is my simplicial complex. I've labeled one of these red with this orientation, and I can propagate with the up Laplacian. I can propagate with a down Laplacian, and I could propagate with both. This should look more flow-like. This should look more curl-like. And these may possibly look more harmonic-like, but, you know, at least we get something. But anyways, but these are things we're still trying to understand, okay? And with that, let me actually tell you some open problems.
Do you have all the triangles there?
I'm sorry?
Do you have all the triangles?
Do I have all the triangles? What do you mean by that?
The triangle faces, do you have?
Oh, I was only propagating edges, so I wasn't propagating the faces. Okay? But yeah, this is a triangular, these are triangles, right? Yeah, I didn't draw them in. I'm sorry, yeah, I should have drawn them in. So one open question is, how does a combinatorial Laplacian converge to the Laplace-Beltramian forms? This one is going to be the next talk. You're going to learn a lot more about point number 2. I think it's really interesting. What is the continuum limit of this random walk? Is it something like Brownian motion on forms? I really don't know, but I'd really want to understanding irreducibility, hitting times, and things like that. And for the Dirichlet walk, I think a lot of things we did can probably be made much nicer by this idea of a Doob transform that Percy had talked about before. But and one of the things that we're still trying to understand is the Cheeger number, both, well, for manifolds, but also for these discrete structures for the middle dimensions. We can tell you something for the top dimension now, and the bottom dimension. The middle dimension, it's still open. And, well, in 1970, Jeff Cheeger said it would be good to understand it. And we're, I guess, still working on it. There are people who gave money, I'm not sure for this. And there are people who I talked to and were helpful. And, yeah, so thank you.
So, I mean, the other way to think of this is the classic way the Laplacians came out was for solving spring mass systems or for solving a heat equation.
Yeah.
So the natural generalization would be Maxwell's equations, right? Electromagnetic radiation. So, and in some sense, you're doing that, right? I mean, but you never mentioned that. So,
I did never mention that, and so...
And in some sense, it probably works nicely when there is a natural analog of electromagnetic radiation. You have flow on the edges, which induces magnetic fields, which induces, and so you should be having two things, you know, a magnetic term and an electrical term.
So, okay, so...
And in your examples, you talked about those, but you didn't use those words.
I didn't. So I'm really a horrible physicist, but more seriously, it's there. And if you look at some of my colleagues, like people like Anil Hirani, he does think of things that way. And some of them, you know, if you also look at some of the things that maybe I shouldn't put words in Pablo's mouth, but, you know, you also think a little bit, right? Or
Game case.
in the game case, yeah, in the game case, right? So there is that kind of perspective there. And when you look at the one Laplacian, it's very much there. You really are looking at curls. All of that is very implicit there.
Even the zero Laplacian, then you're looking at electromagnetic radiation,
yeah.
potential energy versus...
Sure. And you know, there's Maxwell's equation. You have the Dirichlet boundary condition form, like the heat equation, right? So those are all there. And I mean,
That's a Hodge Laplacian.
I'm sorry?
That's a Hodge decomposition.
That's a Hodge decomposition, right? So yeah, absolutely, those are all there. I guess the question is, why didn't I use those terms? I don't know. Physics is hard for me, maybe. I don't. But I mean, it's very fair. And I mean, what I will say this is, me and my colleagues, we really do think moving back and forth between the discrete perspective and the continuous perspective. And that's been very helpful in getting some intuition. So I will say we certainly do that. And I mean, and in some of these papers I read, when I look at the Hodge decomposition, and you look at the very physics versions of this, you read these papers and you can start making those exact connections. I just used this language.